So let F subset of E be a field extension, okay, and alpha be a element of E. Then for any elements A and B in F with A not equals to 0, prove that. So if you take the field F and you attach alpha, so this is basically same as the field F, and if you attach A alpha plus B, right? So you have to prove this. So here A and B both are elements of F. This says that F absorbs its own elements. So this is something very useful. So we will see later why it is very useful. But let's see the proof. So it is not also very difficult to see. So remember that alpha is an element of E, not F. But A and B are elements of F. So we need to prove these two sets are equal, right? So the usual way we do it, we will prove that both of these are subsets of each other. So one side is trivial. So since alpha belongs to F alpha and A comma B belongs to F, so that will imply F of A alpha plus B subset of F alpha, right? Because this is the smallest field containing A alpha plus B, and this is a field which contains F as well as A alpha plus B. So this is the subset. Okay, let me write one more step. So this implies A alpha plus B belongs to F alpha, right? And F alpha contains F also. So F alpha contains this field. Now the other way. Conversely, so we need to prove that F alpha subset of F of A alpha plus B, right? So we need to use that F of alpha is the smallest field containing F and alpha. Conversely, now alpha can be written as, so this is 1 by A times A alpha, because A is not equals to 0, so we can multiply it with the inverse of A, which is 1 by A, and we can write it as plus B minus B by A, and this element clearly belongs to F of A alpha plus B, right? So alpha belongs to F of A alpha plus B, so that will imply F subset of A alpha plus B, and alpha belongs to F of A alpha plus B. So that will imply F of alpha subset of F of A alpha plus B, because F alpha is the smallest field smallest field containing alpha and F. So we have the both the containments. So from this we can conclude the result. So F of A alpha plus B is basically same as F of alpha. Okay. So is the proof clear? So you just need to use the definition of this F attached with an element. So I hope it is fine. So let's see one small use of this thing. Okay. So we all know that. So if you attached Q with root 2, then what is the degree of this extension Q root 2 over Q, right? So this is basically 2. So that is something we all know. This is very basic. But what happens if we attached Q root 2 plus 3? Then what is the degree of this extension? So this is also 2 because 3 is an element of Q itself. So it will get absorbed, right? So basically Q of root 2 plus 3 is same as Q root 2. So we will see more applications of this. This is a very useful fact. So Q of root 2 plus 3 is same as Q root 2. So that will imply degree of this extension is equal to 2. Okay, so let's move on to the next problem. Okay, so again let F subset of E be a field extension and alpha belongs to E be an algebraic element over F. Be an algebraic element over F. Right? So that means alpha satisfies some non-zero polynomial over F. That is the definition of an algebraic element. So prove that alpha and 1 plus alpha inverse has the same degree. So degree of an algebraic element means degree of that irreducible polynomial of that corresponding element, right? So this problem says that if you take an algebraic element, then algebraic element alpha, then the element 1 plus alpha inverse is also algebraic and the degree is same. So I hope you have understood this problem. So how to prove this one? So we need to prove degree of alpha and degree of 1 plus alpha inverse both are same. Means if you take the irreducible polynomial of 1 plus alpha inverse and the irreducible polynomial alpha, the degree of both polynomials are same. That is what we have to prove. But that can be proved in other ways. So let's see how to prove this. So what is degree of alpha over F? So this is basically the same as degree of this extension f of alpha over f, right? Because alpha is algebraic element. And degree of 1 plus alpha inverse over f. So this is f of 1 plus alpha inverse over f. We need to prove these two things are equal, right? How to prove this? So we basically prove that these two fields are equal. Now 1 is element of the field f, right? So it will get absorbed. Since 1 belongs to f of 1 plus alpha inverse is equals to f of alpha inverse. So this is by the previous problem. So now we need to prove that f of alpha inverse is basically same as f of alpha. So our claim is f of alpha inverse is equals to f of alpha. But this is something very trivial, right? So let's let's prove that each of these are subsets of each other. So first let's prove this side. So alpha belongs to f alpha, and f alpha is a field, so its inverse is also in f alpha. So that will imply alpha inverse belongs to f alpha and f subset of f alpha. So f alpha will contain the smallest field f of f alpha will contain the field f of alpha inverse, because this is the smallest field containing f and alpha inverse, and this is a field which contains f and alpha inverse. So one side is clear, other side is also same. So alpha inverse belongs to f of alpha inverse. So that means alpha inverse and its inverse, which is basically alpha, belongs to f of alpha inverse. So alpha belongs to f of alpha inverse and f subset of f of alpha inverse. So that will imply f of alpha subset of f of alpha inverse. So our claim is proved. So from this we can conclude that f of alpha is f of alpha inverse. This is basically f of 1 plus alpha inverse. And from this we conclude that this degree of f of alpha over f is same as degree of f of 1 plus alpha inverse over f. And this is the degree of alpha over f, and this is the degree of 1 plus alpha inverse over f. So this is what we wanted to prove. So is it okay? Okay. Okay, let's move on to the next problem. So let alpha and beta be two real numbers such that alpha and beta both are algebraic elements algebraic over the field Q. Okay, so we are taking two algebraic elements over Q. Sorry, transcendental element, not algebraic. Okay, so they are not algebraic. So prove that either alpha times beta or alpha plus beta is transcendental over Q. So if you have two transcendental elements alpha and beta over Q, then either their product or their sum um, has to be transcendental. Both cannot be simultaneously algebraic. So that is what we have to prove. So can you do it, or do you have some idea how to do it? So for example, you can take pi and you can take e, right? Both are known as that these two elements are transcendental over Q. That is something going on. So from this you can conclude that either pi plus e or pi times e. So in these two elements, one has to be transcendental. So that is something you can conclude. So let's try to prove this. Yeah, do you have some idea? Okay. So we will prove it by contradiction, right? So suppose both are algebraic. Suppose alpha beta and alpha plus beta both are algebraic over Q, right? So then we have to arrive at some contradiction. It is given that alpha and beta both are transcendental. So that is something which that is something we have to use. So we know that if you take a field F and if you take an extension of it, then all the elements of E which are algebraic over F forms a field, right? So that is something which we have done in the lectures. So this fact we will use. So now alpha beta and alpha plus beta are algebraic over Q. That will imply that alpha plus beta square and 4 alpha beta are algebraic over Q, because product of algebraic elements are algebraic and sum of algebraic elements are algebraic because they forms a ring, they forms a field. So alpha plus beta square minus 4 alpha beta is also algebraic over Q. right? Now what is this element? So this is basically alpha minus beta whole square is algebraic over Q. So from this we can say that alpha minus beta is algebraic over Q. So that means if some element A is algebraic, okay, let me write it in the black. So if A belongs to R is algebraic over Q, then that will imply square root of A is also algebraic over Q. So this is something which we are using. So I will prove it separately. Let's not worry about that. So alpha minus beta is algebraic over Q. And we have also alpha plus beta is algebraic. So alpha plus beta and alpha minus beta are algebraic over Q. So that will imply their sum. Their sum is 2 alpha is algebraic over Q. And 2 is in Q, right? So we can multiply by the inverse. So that will imply alpha is algebraic over Q. So this is a contradiction because alpha is a transcendental element. So either alpha times beta or alpha plus beta is transcendental over Q. So is it okay? Do you have any doubt in this? So I will prove this part. That will be a separate problem. That's not difficult actually. Okay, let me do it now. So it is problem 5. So let A belongs to R be algebraic over Q, then prove that the square root of A is also algebraic over Q. So this is not difficult to see. So since alpha is algebraic, we take a polynomial which has a root A. So let Px equals to summation uh, let's say bi x power I equals to 0 to n belongs to qx, a non-zero polynomial, non-zero polynomial such that p of a is equals to 0. So since a is algebraic, we can choose a polynomial like this. So now uh, so summation bi a power I equals to 0 to n is 0, right? So this you can write it as summation bi square root of a whole power 2I equals to 0 to n. This will be 0. So that will imply q of root a is equals to 0, where qx is equals to summation bi x power 2I I equals to 0 to n. This is also a polynomial in qx, right? Because the coefficients are from q. So root a, square root of a is a 0 of the polynomial q of x. So that will imply root a is algebraic over q. Is it fine? So if you take an algebraic element over q, its square root is also algebraic. So are you following, or do you have some doubt? So if you have any doubt, just feel free to ask, or you can put it in the chat box also. So from this fact, we also say something more. So let me put that as remark. So A is algebraic. From that we have concluded root A is algebraic. So we can use this fact recursively, right? So root A of root A is algebraic. This is, that means fourth root of 2, fourth root of A is algebraic. So A belongs to R is algebraic over Q. That will imply if you take the 2nth root of A, that is also algebraic over Q. So that is the more general part. So this fact which we have used in the earlier problem, now that should be clear for you. But still, if you have any doubt, just feel free to ask. Okay. So here, okay, something more general we can talk. So here we are taking the 2nth root of A, right? Now what about the other powers? So this is problem number 6. So let A belongs to R be algebraic over Q and R be another rational number. Then prove that A power R is also algebraic over. So if R is an integer, then it is clear, right? Because set of all algebraic elements forms a field. So product of algebraic elements are algebraic. So if R is integer, then that is clear. But we are taking R is rational number. So we are saying if R is rational number, then also the rational power of a real number is algebraic. Okay. So since R belongs to Q, so let R equals to P by Q, where P belongs to Z and Q belongs to N, Q not equals to 0. Right. Now, A is algebraic over Q. So that means A satisfies some non-zero polynomial over Q. So P of A equals to, sorry, not P, let's say F of A equals to 0 for some non-zero fx in Q of x. So this is the definition of algebraic element. So let's say fx equals to summation fi x power I equals to 0 to n. So that means summation fi a power I equals to 0 to n is 0. So from this we can conclude that summation fi a power 1 by q whole power qy, it is 0. The same trick which we have used in the earlier problem. So that means a power 1 by q is algebraic over q. Now this is a non-zero polynomial, right? Because the coefficients are non-zero. So a power 1 by q is also algebraic over q. So we can take a power 1 by q times a power 1 by q times a power 1 by q up to p times. So this product is also algebraic over q, because product of algebraic elements are algebraic. Now what is this? This is just a power p by q. So a power p by q is also algebraic. So this completes the proof. Is it fine? Did you got the proof, or okay? I hope others also got the proof. Okay, so let's move on to another problem. So one thing, recall that. So suppose you have an extension F subset of E and you have an algebraic element over F, right? Then we all know that F of alpha over F, it is a finite extension, right? So that means F of alpha is a finite dimensional vector space over F. So what is the, can you give some basis for that vector space? So if this degree is particularly n, then 1 alpha up to alpha power n minus 1, this is a basis of f of alpha over f. So this is something you can find in the lectures, right? So this is very useful, you should remember this. So let's use this to prove the following problem. So this problem has two parts, so let's write it down. Prove that the degree of this extension, okay, not degree, prove that q attached with pi is a finite extension of q attached with pi q, and also find a basis for q of pi as a vector space over q of pi q. Vector space over q of pi q. So in general, q of pi, it is transcendental over q, right? That is something we know because pi is transcendental element. But instead of q, if we take q of pi q, then it will be an algebraic extension. Not only algebraic, it will be a finite extension. So can you prove this? It is finite, or at least can you guess the degree of the extension? So here we have the tower. If you take q of pi, here you have q of pi q, and here you have q. So we are saying this extension is finite. So how to prove this one? So q of pi is basically q of pi q comma pi, right? Because pi q is in q of pi. So this is basically q of pi q attached with pi. So you just need to prove that pi is algebraic over this field. So since pi is a root of the polynomial, let's say xq minus pi q belongs to q of pi q x. So q of pi is algebraic over q of pi q. So there is nothing to do. So did you got the idea? So basically, when we say f of alpha is finite over f, if and only if alpha is algebraic over f. So that is the same thing which we are using here. So q of pi q attached with pi is algebraic over q of pi q because pi is algebraic over this field. And so this degree, we can say it is less equals to 3, right? Less equals to 3 means it has to be divided 3. So it can be 1 or 3. So it is less equals to, it divides 3 because it satisfies a polynomial of degree 3. So that means it can be 1 or 3. But it cannot be 1 because pi does not belong to this field. So it has to be 3. So that is something trivial. So this is 3 because pi does not belongs to q of pi q. So it is a finite extension and degree of the extension is 3. Now can you find a basis? So let me write it here. So this is actually q of pi cube and you attach it with pi. Now what about the second part? So we already know the basis of f of alpha over f, right? When alpha is algebraic. So can you use that one to find a basis in this case? So basis of f of alpha, so let me recall it once more. So basis of f of alpha is 1 alpha to alpha to the power n minus 1, right? Where n is the degree of the extension over f. So what will be the basis in this case? So since this degree is 3, so 1 pi square is a basis of q of pi over q of pi cube. So I hope you understood this. Yes, so far, do you have any doubt? Yeah, you can ask.
What is the degree of q of root 2 plus root 3 over q of root 2?
So we are asking degree of q root 2 plus root 3 over q of root 2. Is it you are asking? Is that the same thing you are asking?
Yes, sir.
So I think it is easy because this field is actually q of root 2 comma root 3, right? So you can treat it as q of root 3 and attached with root 2. So you just need to find degree of this extension. Okay, the other way. Root 2 here and root 3 here. So you just need to find degree of root 3 over q root 2. So you understood? So this is q of root 3, q of root 2 attached with root 3. Yeah. So now can you do it or still you have doubt? So you just need to find the degree of root 3 over q of root 2. So what will be the degree of the irreducible polynomial of root 3 where the coefficients are from q of root 2? Yeah. Okay. Okay. So Okay, any other doubts? So if no, then let's do some problems on the degree of the extension. I hope then it will be much more clear. So problem number 8. So find the degree of the following field extensions. So let's start with this. Okay, first let's find the irreducible polynomials. So let's do it step by step. Find the irreducible polynomials in the following cases. Okay, so first one is, so you take cube root of 2 plus cube root of 4. So this is an element of R. So find it over the base field is over Q. So what is the irreducible polynomial of this element over Q? The second thing is 1 plus, just attach 1. 1 plus cube root of 2 plus cube root of 4. So this is an element of R over, so find the irreducible polynomial of this element over Q. And let's take one more. Let's take root 2 times I. So this is belongs to C. So find it over Q. So in the following three cases, we need to find the irreducible polynomials. So can you try for the first one? Just try it yourself. So first thing, that this element is definitely algebraic, right? Because cube root of 2 is algebraic and cube root of 4 are is also algebraic. So their sum is also algebraic. And this is algebraic because it is a root of xq minus 2, and this is because it is a root of xq minus 4. So these two elements are algebraic. So its sum is also algebraic. But from these two irreducible polynomials, we cannot find the irreducible polynomial of this sum. We need to do it separately. So just think it for probably few seconds. So first we should try to find a polynomial which has a root as this element. Then we will check that polynomial is irreducible or not. So can you find a polynomial which has a root uh, exactly equals to this element? So let me do the first one, or probably the third one, which is the easier. So first I will do the third one. So from that you will got some idea. So we need to find an irreducible polynomial for this element, root 2 times I. Okay, so let x equals to root 2 times I. So if we square both sides, then what you will get? So x square is minus 2, right? So that will imply x square plus 2 is 0. So this element root 2i, the root of this polynomial. So root 2i is a root of x square plus 2 belongs to, it is an element of zx, right? And this polynomial is irreducible, right? We can use the Eisenstein criteria, which is irreducible in Q of x by Eisenstein's criteria. So x square plus 2 is the irreducible polynomial of root 2 times I. So this is the most simplest part of these three problems. Now what about the first one? Can you try with the same method? Or can you give me some polynomial which has the cube root of 2 plus cube root of 4? Yes, any answers? Okay, so let's do the first one. So here also let x equals to cube root of 2 plus cube root of 4, right? So then it will imply that x equals to, so we just need to simplify it. So this is cube root of 4. So we can take cube root of 2 common. So this will be 1 plus cube root of 2. Now let's take cube power both side. So x cube, here you will get 2 and plus 1 plus cube root of 2 whole cube. Now let's break this. So this, from this you will get 1 plus 3 times cube root of 2 plus 3 times 2 power 2 by 3, right? And plus 2. Now what is this? This is basically 2 times 1 plus 2 is 3 plus 3 times cube root of 2 plus 3 times cube root of 4, right? Now again simplify this. So from this we can write x cube equals to, so we can take 3 common. So it is 6 times 1 plus cube root of 2 plus cube root of 4. But this element is simply x here. So let's substitute this. So xq equals to 6 times 1 plus x. So that will imply xq minus 6x minus 6 equals to 0. So we got a polynomial which has a root cube root of 2 plus cube root of 4. Now is it irreducible? Can you check? So is it an irreducible polynomial in q of x? So cube root of 2 plus cube root of 4 is a root of x cube minus 6x minus 6, which belongs to q of x. So we need to check it is irreducible or not. If it is irreducible, then we are done. So can we use the Eisenstein's criteria here? Okay, so since x cube minus 6x minus 6 is irreducible in q of x by Eisenstein's criteria, so you can take prime 2 or 3, both will work in this case. So by using the Eisenstein's criteria, this polynomial is irreducible. So it is the irreducible polynomial of cube root of 2 plus cube root of 4 over q. So is it fine? So I hope it is fine. So the only part left is the part B. So we have just attached one. We have one additional part 1 in the first case. So what to do in this situation? So can you try it on your own? Just think it for a few seconds. So in the lectures, if you can recall that, so we have find the irreducible polynomial for root 2 plus root 3 over q, right? So the same method you can use for the part B. So just try it. Yeah, did you got any polynomial? So let's do this. So again we will follow the same idea. So let x equals to 1 plus cube root of 2 plus cube root of 4, right? Then we can write it as x minus 1 equals to, again we can take cube root of 2 common, so it will be 1 plus uh, cube root of 2. Now let's take powers both sides. So x minus 1 cube will be 2 times, so again the same thing, so 1 plus 2 plus 3 times cube root of 2 plus 3 times cube root of 4, and in the left side x cube minus 1 uh, plus 3x minus 3x square. So the right hand side it is 6, so we can take 3 common, so it is 6. 1 plus cube root of 2 plus cube root of 4, but in this case we have this element is x, so let's substitute this. So this is 6x, so x cube minus 3x square minus 3x minus 1 is 0. So this element is a root of this polynomial, so we need to check this is irreducible or not. So 1 plus cube root of 2 plus cube root of 4 is a root of x cube minus 3x square minus 3x minus 1 belongs to q of x. So since the constant term is 1, we cannot use the Eisenstein's criteria here, right? So how to check it is irreducible or not? So do you have any idea how to do it? So our goal is to find the irreducible polynomial of this element, right? So uh, so can you tell me the degree of the irreducible polynomial at least? Okay, let px belongs to qx be the irreducible polynomial of 1 plus cube root of 2 plus cube root of 4 over q. So px is the irreducible polynomial and this is an arbitrary polynomial which has a root 1 plus cube root of 2 plus cube root of 4. So px must divide this polynomial, right? So that will imply px must divide x cube plus 3x square minus 3x minus 1, because both these polynomial are in the evaluation map from q of x to q, you just attach that root. So if you take this as evolution map phi, so both this polynomial belongs to that kernel of phi and px is the generator of that kernel. Now what is the degree of px? So now degree of px is same as the degree of this extension, right? 1 plus cube root of 2 plus cube root of 4 over q. So what is the degree of that of this extension? Yes, anyone? So this degree is actually same as the degree of cube root of 2 plus cube root of 4 over q, right? So go back to the first problem. So sorry, second problem. 1 is an element of q, so it will get absorbed. So these two fields are equal. So this degree of these extensions are also same. So what is the degree of this extension? So degree of this extension, so you need to go back to the first problem. So degree of this extension is the degree of the irreducible polynomial of this element. So what was that? So that is in the first problem, right? We got a degree 3 polynomial which was irreducible. So this degree is basically 3. So Px has also degree 3 and this polynomial has also degree 3. And both are monic polynomials. So what can you conclude? Thus, Px must be equals to x cube minus 3x square minus 3x minus 1. Since both are monic polynomial of degree 3 and one divides the other, they has to be equal. So this is the irreducible polynomial of the required element. So we are indirectly proving that this is an irreducible polynomial. So is it fine? Okay. So hence, okay, so this completes the proof. So this is a very indirect method, but it's useful. So if it is fine, let's find some degree of extensions. It is problem number 9. Okay, so find the degree of the following field extensions. So we need to find the degree of the extensions. So the first one is, so you take the field Q and attach 3 plus 2 times root 2. Find degree of this field over Q. And second one is, you take Q and attach 1 plus square root of minus 3 plus square root of 1 minus square root of minus 3. So you attach this element with Q and find the degree over Q. So just let's do these two extensions. Yeah, so try the first one. So we need to find the vector space dimension of this over, and same for the second problem. Yes, any idea how to do it for the first one? So you just need to find the uh, irreducible polynomial of this element, the degree of that irreducible polynomial, right? So what will be the irreducible polynomial of cube root of 3 plus 2 root 2? So okay, let's do the first one. So observe that 3 plus 2 root 2, this element is basically, you can write 1 plus 2 times root 2 plus 2. So that means it is, if you take 1 plus root 2 and if you take the square and then take the square root. So this is basically 1 plus root 2. So q attached with 3 plus 2 root 2 is same as q of 1 plus root 2, and it is basically same as q root 2, and we know the degree of q root 2 over q, right? So degree of this over q is degree of q root 2 over q, and which is 2. So you just need to observe this fact for this first problem. So is it okay? So I hope it is okay. So let's do the second one. So in the second problem, we need to find degree of this element, right, over q. So let x equals to square root of 1 plus square root of 3 plus again square root of 1 minus square root of, sorry, minus 3, right? Now if we take squares both sides, then what happens? So if we take square of this, so it will get, we will get square of this plus square of this plus 2 times the product. So we'll get 1 plus square root of minus 3 plus 1 minus square root of minus 3 plus 2 times, uh, if you take the square root, 1 plus root minus 3 times 1 minus root minus 3. So here square root minus 3 will get cancelled. So this is basically 2 plus 2 times. So this is a complex number, right? And it is the conjugate of that complex number. So we are taking z times z bar and square root of that. So that is basically same as mod z. Yeah, anyone has any doubt? So what is the modulus of this complex number? So this is basically, if you take,
Two.
yeah, you're right. So this is 1 plus root 3I. So this is, so we are getting x square minus 6 equals to 0. So this element is a root of this quadratic polynomial and it is clearly irreducible, right? So you can use the Eisenstein criteria again. So degree of q 1 plus square root of minus 3 plus 1 minus square root of minus 3 over q is 2. Yeah, is it fine? Okay, so let's move on. So we can take the field of extensions q subset of R, right? So R is an extension of q. So we can ask the dimension of R as a vector space over q. So the degree of extension R over q. So can you say what is this vector space dimension? So this is something you must have done in your linear algebra course. So do you know what is dimension of R as a vector space over q? Okay. So actually it is an infinite dimensional vector space over q. So you can prove it by the fact that q is countable but R is uncountable. So using that fact you can prove this. But here we will do it by some other method. Okay, so let's do this. So prove that the degree of the extension R over Q is not finite. Okay, so this extension is an infinite extension. So how to do this? So so recall that. So we have earlier proved that uh, for okay, so for every positive integer n greater equals to 1, there exists a irreducible polynomial, let's say pnx in qx of degree n, right? And what was that polynomial? It was x to the power n minus 2. So it is a polynomial of degree n in qx which is irreducible. So recall that x to the power n minus 2 belongs to qx is irreducible polynomial of degree n. And what is the root of this polynomial? Is nth root of 2, right? So if you take q and attach the nth root of 2, so degree of this extension is basically n, because x to the power n minus 2 is the irreducible polynomial of nth root of 2. right? And this is for every n. So you can take n as large as possible. So, okay, not again. So this implies Q of nth root of 2 is a subspace of R of dimension n. So you can take n arbitrarily large, right? So this vector space R has arbitrarily large, has a subspace of arbitrarily large dimension. So it cannot be a finite dimension. So R cannot have finite dimension over Q. So did you got the idea? It's very easy actually, rather than the countability argument. So is it okay? So dimension n over Q means the vector space over the field Q. So I hope you also know the countability argument. Okay, so let's move on. Okay, let's do a critical problem. So let F subset of E be an algebraic extension. That means every element of E is algebraic over F. And suppose uh, R is a ring such that F subset of R subset of E. Then prove that R is a field. So if you have an algebraic extension and if you have a ring in between the fields, then that ring has to be a field. Here you have E and here you have F, and this extension is algebraic. And in between you are taking a ring. So this says this ring R has to be a field. Think it for a few seconds. So what we have to prove in this case? So just try to think step by step. So we need to prove R is a field, right? So that means we need to prove uh, every non-zero element of R is a unit. And what is given here? So given is this extension is algebraic. So that is something we have to use. So how to use this fact? So we want to show R is a field. So let's take a non-zero element. So let 0 not equals to R belongs to R. So we need to prove R is a unit. Now R subset of E, right? So that means R belongs to E, since R subset of E, and E is a field. So R inverse exists in E because E is a field. But E is algebraic extension of F. So R inverse must be algebraic over F. So R inverse is algebraic over F. So R inverse must satisfy some non-zero polynomial over F. So we can take a monic polynomial in that case. So that means R inverse power n plus a n minus 1 R inverse power n minus 1 plus dot dot a1 R inverse plus a0 equals to 0 for some an minus 1 an minus 2 dot dot up to a0 in F. Right, up to this I think it's clear. So what is this? So this is R power minus n plus a n minus 1 R power minus n plus 1 plus a n minus 2 R power minus n plus 2 plus dot dot so on a1 R inverse plus a naught equals to 0. So what is our goal? Our goal is to show R is invertible in capital R, right? Means we need to show R inverse belongs to R. So that is our target. So from this, can we prove that R inverse belongs to R? So can you conclude this thing from here? Okay, let's multiply R to the power n minus 1 both sides. Then what happens? So let's multiply R to the power n minus 1 the both sides. So here you will get R to the power minus 1 plus a n minus 1 times 1 plus a n minus 2 R plus dot dot plus a1 n minus 2, sorry, uh, a1 R power n minus 2 plus a0 R power n minus 1 equals to 0. So that will imply R inverse equals to a n minus 1 plus a n minus 2 times R plus so on a0 r power n minus 1. Now these coefficients ai belongs to f, which is subset of r, and r is also in r. So this thing must belong to r, because f is subset of r and r belongs to r. So that will imply r is an unit in r. So r is a field. Is it okay?
Yes, sir.
Okay. So so far, do you have any doubts? Okay, so I think I have done all these parts except the field homomorphism. So I think we can do that in the next session. Okay, anyway. So
Sir, there are problems in assignment on this field homomorphism.
yeah. So do you have particular any doubts or any specific questions?
That question only. If you can give a brief idea about what is field homomorphism, so that we can go through that problem and we can able to solve.
Yeah.
Or if
So
possible, if you can take that problem itself, that would be a great help.
yeah, actually, I have not go through the assignments. So basically, field homomorphisms are in our particular context. So if you have two fields, let's say A and E, and if you have a homomorphism, so how the algebraic elements behave under this homomorphism, right? So that is the particular thing which we are looking in our course. I think all the problems are related to these things and how to extend the homomorphisms. So I think that is doable from the part what has been taught in the course. So other than that, do you have any other doubt? So if you did not understood the question in the assignment, then you can ask. I can try to explain.
Sir, one question is there.
Yeah,
It is like if M and A, B are
yeah,
arbitrary positive integers
okay,
and nth root of A and mth root of B,
yeah,
and if alpha is equal to sum of nth root of A plus mth root of B,
okay.
uh, then s- then what can you say about this degree of alpha?
Yeah, I think I have done one similar question in this, right? So you can try to guess it from here.
Uh,
So yeah, this problem.
which
Part
one?
A and
Just
part B. Yes, I think it's
okay,
similar.
this one.
Yeah, so you can
Okay,
try to
can you
guess it.
just scroll down a bit?
Yeah, is it a assignment problem or?
Assignment problem only, sir. Is it
Okay.
assignment problem?
So yeah, try to see it via examples.
Try to solve by Eisenstein criterion or like this. Okay.
You need to guess some formula for the degree, right?
Hmm.
So I have done one example here. So you can try to guess it from here, or you can try some more examples.
Sir, excuse me. Sir,
Yes.
could you explain the primitive root polynomial or primitive
Yeah,
unity?
primitive polynomial. So if you take a polynomial, let's say fx, it looks like a0 plus a1x plus dot dot an x power n, let's say from zx. So this is an arbitrary polynomial. So we call it primitive. So f is primitive if you take the GCD of the coefficients a0 up to an, if the GCD is 1, then we call it is a primitive polynomial. Yeah, is it okay? If the GCD of the coefficients is 1, then we call it a primitive polynomial. Yeah, is it did you got the definition, or do you still have doubt? One more. What do you mean by one more? So, so what is your doubt exactly? So, okay, let me give some example maybe. So you can take 2x square plus 3x plus 5 belongs to zx. So it is a primitive polynomial, right? Because CD of 2, 3 and 5 is 1. So yeah, if the GCD of the coefficients is 1, then it's primitive. So by using this, you can construct many more examples. Is it fine? Okay. So anything else?
Sir, please show the questions that you have solved. Cube root of 2 and cube root of 4 or something like that.
Yeah. Do you have
Yeah,
some doubt in that?
just about that. Ah, yes, this one, sir.
Yeah.
I
Just
just want to see to it. Yeah,
so I will
yeah.
upload the
Thank you, sir.
solutions also, so you can check it from there.
All right, sir. Thank you.
Yeah. Anything else?
Sir, the exam that we are going to appear on 23rd of March, it is going to be computer-based exam, no, or pen or paper?
Yeah. Actually, I don't know. Actually, I think it should be mentioned in the course page, right? You should check it from there.
All right,
Yeah. I think it should be there.
all right. And I just want to ask whether the question will be all MCQ type, just like we had in the assignments, or a combination of MCQ and MSQ, true,
Uh,
false.
Maybe it can be combinations. I'm not sure. I think they will let you know, or if not,
If you
then
can had a word with the course coordinator,
you can
and
put it in the
next week it
discussion
is
forum.
going to be the final interaction, na sir?
Yes,
So
yes.
if you
So
can explain or
uh,
you can pass on the information, that would be
yeah, but
a
you
good
can
help for us because we are going to write the exam.
yeah, yeah. So you can put it in the discussion forum. So they will.
Yes, sir. Yes, sir. Me too have a same doubt because it's a single answer question or multiple answer question. One or more options will be right like that way. That is in the similar to assignment.
Yeah, I think it should be similar to assignments. I think.
Similar to assignment is okay, but two more options or one or more options means it is little bit tough, no? So
Very
usually
tough.
MCQ means it's a single answer only, no?
Yeah, yeah. But look, I cannot say about that. But if you
Okay,
still have
you
doubt,
can't say, but you have a discussion with that. Kindly confirm it whether it is the same type as in the pre that is assignment type.
Yeah, look,
That
I can
alone we need.
contact, but the fact is, we can put it in the discussion forum, so they can give better explanation for that. Okay, so and you will get
Sir, what
response
happen is
quickly.
when we put questions on the discussion forum na, so most of the time it is observed that hardly anyone reply to that. I have earlier also posted, and after so many days, I got a reply. So
Is it
discussion
so?
forum should be used throughout the course. That will
Yes.
really enhance the number of registration in the next semester. Otherwise, what happened? Very few opted for this course, and they find it very difficult, and then they how can we refer this course to the other friends of ours? So
Look,
these are the things that we have.
I think they reply earlier as soon as possible. But okay, let me check also. You just put it in the discussion forum. I will mention there also, so that
All
it should
right,
not
sir. Because
forget
these
me.
are the queries, and next week it is going to be the final interaction. So
Yeah,
we
yeah.
want
So we have,
it should be done before that. That's why we have asked the question now.
yeah, yeah. It's don't worry. We
Excuse
have,
me, sir. One more doubt. That is in the live session, uh, the drive is shared to us.
yeah.
That live session, the previous session was missed.
Uh,
Uh,
no, I think I have
if the
uploaded that. You can check it now.
Oh, you have updated. Okay, last
Yeah.
scene, I think last 2 days before I saw it, so
Uh,
that's why I asked.
yeah, yeah.
Thank you,
No,
sir.
I
Thank you,
have
sir.
updated that one now. You can check it. Yeah. So all of these PDFs would be there. Yeah, don't worry. Just
Okay,
put
sir.
that
Thank you very
in the
much.
yeah, put that in the discussion forum, and we will get back to you soon. Don't worry.
Thank you, sir. Thank you so much.
Yeah,
Sure, sir. Sure. Thank you.
yeah. Okay. Bye then.